I now take up chapter 9. It is single variable optimization, and we start with some basic definitions. Here, if we get back to what we studied in chapter 7, there if I talk about f of x, and let's say this has domain D. Now in this case, when I write C belonging to D, it is a maximum point for f This is if and only if, when I think of f of c, that is greater than or equal to f of x for all x belonging to D. So this is if and only if f of x less than equal to f of c for all x belonging to D. That means C belonging to D would be the maximum point for f. That gives us the maximum value as far as the function is concerned. And similarly, if I think of D belonging to that domain D, this is a minimum point for f. So please get this right, that when I talk about maximum point or minimum point, I'm concerned about the points in the domain. Those points, so if I talk about a maximum point, that means I'm concerned about that point in the domain which gives us the maximum value. If I'm talking about a minimum point, so that point in the domain which gives us the minimum value as far as the function is concerned. So D belonging to D is a minimum point for f if and only if f of x is greater than equal to f of D for all x belonging to capital D. Minimum point, and that's a maximum point. So in this case, as far as if I talk about f of c would be, this is the maximum value of the function. This is called the maximum value, and here f of D would be the minimum value. So f of c is the maximum value, f of D is the minimum value. Here we have written less than equal to, and here I have written greater than equal to. But now let's say if I have a point C in the domain and the value of f at C is strictly larger than any other point in the domain. So if f of c is greater than f of x, here I have written greater than equal to f of x. But if the value of f at c is strictly larger than at any other point in D, than at any other point in the domain, then we would write f of c greater than f of x for all x belonging to D. And in that case, little c is not the maximum point, but we then call it a strict maximum point. And if in this case, again here, if let's say if f of x is greater than f of D, so that means the value of f at D is strictly less than at any other point in the domain, then we obviously write f of D, or then we write f of x greater than f of D for all x belonging to D, for all x belonging to the domain. In that sense, we call D not the minimum point for f, we call it a strict minimum point. But we have to keep this in mind in this case, so let me just write this, that if f of x is or let me write if f of c is greater than f of x, for all x belonging to D, x not equal to c. So if the value of f at c, what it means is that if the value of f at c is strictly larger than at any other point in the domain, then c is a strict maximum point. On the other hand, if f of D is less than f of x for all x belonging to the domain x not equal to D, that means if the value of f at D is strictly less than at any other point in the domain, in that case, then D is a strict minimum point. Then D is a strict minimum point. And when we talk about these, so C and D are strict maximum points, or C and D, C is a strict maximum point. Earlier we talked about C being a maximum point. Then we talked about D being a minimum point, or D being a strict minimum point. And if now in this case, if C is a maximum point, f of C is the maximum value. If D is the minimum point, f of D is the minimum value. Instead of all this, so instead of thinking of a maximum value, maximum point, minimum value, minimum point, we also call this, so collectively we can actually think of optimal values. When I write maximum value or minimum value, I can actually write optimal values, or I can write extreme values. And corresponding to a maximum point or a minimum point, collectively I can write optimal points, and here I can write extreme points. Now, let's say f is a function with domain D. Then if I want to now think of minus f, that means I can write, I know that f is a function which is defined in the domain D. Then minus f, it will be defined in D by this, is defined in D by minus f of x. Earlier it was f of x, but now it would be minus f of x. So that means it would be this, and this would be nothing but minus f of x. So the point I'm trying to make here is, let's say f is any function with domain D. Then if I think of minus f, what it means is I'm actually concerned about minus f of x, and that will be nothing but minus f of x. Now that the point that I'm trying to make here in this case is, so if this is the case, so now let's say if you have a function f defined in the domain D, and you know that f of x is less than equal to f of c for all x belonging to capital T. So what I see here is that C is a maximum point for f. This is if and only if, now I can write minus f of x greater than equal to minus f of c for all x belonging to T. What I mean to say here is that in this case, C maximizes f in D. And this is if and only if C minimizes minus f in D. So the point is, in this case, I can write that C maximizes f in D. I'll show one diagram. If and only if C minimizes minus f in D. And that means we can now get to this. So here we see C maximizes f in D. So C is a maximum point for f of x in this case. And if I go for minus f of x, we can see that C is a minimum point for minus f of x. Because corresponding, so what we see here is that if I just take a look at the upper portion here, I see that f of x is less than equal to f of c for all x belonging to the domain, and this I can see in the upper portion. That means C is a maximum point for f of x. In the lower portion, I see if you look at minus f of x, you see that it is greater than equal to minus f of c. This is minus f of c, and you see that minus f of x is greater than equal to minus f of c for all x belonging to the domain D. So clearly from here you see that C is a minimum point for minus f of x. So that means C is maximizing f in D if and only if it is minimizing minus f in D. The domain remains the same. Alright, now I can take up this point. So here what we are going to do is we are going to determine the possible maximum and minimum points of a function. So if I'm concerned about c and little d, basically we are concerned about how to determine the maximum point of a function or the minimum point of a function. We are actually concerned about how to determine the possible maximum and minimum points of a function. And in this way, I can write this. That if I write about x naught is a stationary point for f if f prime x naught is equal to 0. So think about it this way, when we talk about stationary, that means when I say x naught is a stationary point, that means the function f is not changing when we are at x naught, and that just means that f prime x naught is equal to 0. So geometrically, if we think of the stationary points, they would occur where the tangent to the graph of the function has to be parallel to the x-axis. So if there is an infinitesimal change in the independent variable, if there is an infinitesimal change in x, we don't see any sort of change in y. And that's why when we talk about stationary points, so I can write that stationary points occur where the tangent to the graph of the function is parallel to the x-axis. So if you take a look at this diagram, in this case, what we see is here in figure 9.2, in this case, if we take a look at this and we think of the function having stationary points, the function f, it has some stationary points. So here we see that there are two stationary points, one is C and the other is D. At C there is a maximum and at D we see there is a minimum. If I take up the next diagram, figure 9.3, I see that the function has got no stationary points. The point to note is there is nowhere I see that f prime x naught, wherein x naught lies in the domain of the function. There is no point wherein I see that f prime x naught is equal to 0. And still I see that there is a minimum and there is a maximum. The point to note here is that if we look at the maximum, there is a maximum at this endpoint B and there is a minimum at this D. But I see that at D the function is not differentiable. It's not that I can have a tangent to the, so when I talk about the function being differentiable, that just means we are able to get to the slope of the tangent to the graph of the function at that point. But here we can't. Here you do not have a unique tangent to the graph of the function, and if we don't have that unique tangent to the graph of that function, we can't actually get to the slope of that unique tangent. So clearly at D the function is not differentiable, it is not smooth. But at B also we see that the derivative, first of all here we will actually think of only the left hand derivative. We will only think of this derivative. So here I see that derivative, the left hand derivative, is also not 0. So that is why we see that in this case we don't have any stationary points. In figure 9.3 the function has got no stationary points. We do have a maximum at the endpoint B, and we also have a minimum at the point D, little d. But we see two more points, that at little d my function is not differentiable. At little b the derivative is not 0. When I say derivative is not 0, please keep this in mind that we are talking about the left hand derivative. The left hand derivative is not 0. The left hand derivative is not 0 at little b. If I look at figure 9.4, here in fact there are three stationary points, x0, x1 and x2, because we see this, this and this. What we see here is that if we look at the endpoint A, there is a minimum. But I can't say that the function has any maximum value, because I see that as x tends to b, as x approaches this b, the function, it is actually approaching infinity. You can see that it is approaching like this. So the point to note here is, number one, there are three stationary points, x0, x1 and x2. As far as the minimum of the function is concerned, the minimum point of the function is concerned, that point is little a. But if I think of the maximum point, I can't actually get to the maximum value of f, because I see that as x tends to little b, the function value approaches infinity. If I take a look at x naught, we see that the function has got a local maximum. So at x naught, f has a local maximum. This is something new, but when I say x has got a local maximum at point x naught, this means that its value at that point, its value f, the value of f at point x naught is higher than at all neighboring points. So you see the neighboring points, and we see that the value of the function at x naught is higher than its value at all neighboring points. If I take a look at x1, in the same way I can say that x1, in a similar manner I can say that at x1 the function has got a local minimum. So at x1 f has a local minimum. What I mean to say here is that its value, the value of the function at that point x1 is lower than at all neighboring points. So that neighboring thing is very important here when we talk about local maximum or local minimum. If I take a look at x2, so I can see here that at x naught f has got a local maximum. If I see x1, f has got a local minimum. But if I take a look at x2, we have a stationary point, but there is no local maximum nor a local, there is no local maximum and there is no local minimum. And here x2 will be called an inflection point. So an inflection point is a stationary point. Clearly x2 is a stationary point, but I see that it is neither a local maximum nor it is a local minimum. And x2 is called an inflection point. At x naught f has got a local maximum precisely because the value of f at x naught is higher than at all neighboring points. If I take up x1, I know x1 is a stationary point, but I also see that at x1 f has got a local minimum. What it means is that the value of the function at x1 is lower than at all neighboring points. If I look at x2 is a stationary point, but the point is that it is neither a local maximum nor it is a local minimum. And here x2 is called, that is why x2 is called an inflection point.